Now let's take a closer look at the electronic voting system used by the world's largest democracy. India is an incredibly fascinating place. It's probably my favorite country in the whole world to travel to. Every time I go to India, I learn so much about their culture, and by reflection, so much about my own culture too. In 2010, I got to go to India for a very special purpose, though. I got to take part in what became the first independent security evaluation of the country's DRE voting system. I was joined in this study by Rob Honkrijp, the Dutch hacker and activist who was the man responsible for having the NADAP machines banned in the Netherlands. Rob and I got to have a fantastic adventure and a deeply interesting research project as well. So these are India's voting machines. In India, they're called EVMs, or for electronic voting machine. The machines are manufactured by a pair of companies that are owned by the Indian government. And they were introduced gradually through the 1990s, and then finally adopted nationwide early in the 2000s. The Indian voting machines are most interesting to me because they're just so different from the machines that are used in the US and Europe. While the machines in the US and Europe are very complex devices, the Indian machines could barely be simpler. The machines that we use in the US, for instance, have a design and an internal structure and organization that's very similar to a full-blown PC. But the Indian machines are what we'd call an embedded system, a much simpler version of a computer. Whereas there's been an incredible amount of research by now, study after study, showing security problems in machines used by the US and Europe, countries like India have been almost entirely ignored by the research community. And yet the systems are so different, simple versus complex design, that it turned out they had a lot to teach us. And in the research I'm about to tell you about, we found that the machines used in India are also vulnerable, but in different ways. So let me tell you a little bit more about how the machines work. But before I do, I want you to think about some of the engineering constraints, the design constraints that the machines had to be built to work under. How is voting in India different from voting in the US and Europe? And what sorts of things would engineers have to take into account while designing these machines? So I'm going to give you a chance to think about that before we come back. India's EVMs had to face some really difficult challenges that are quite different from the situation in the US and Europe. One challenge is cost. So the voting machines used in the US, the DREs, typically cost several $1,000s a piece. But India needed to deploy 1.4 million of these machines in order to have enough to count all those votes. There's no way that they could handle the costs of deploying expensive US-style machines. And so the machines used in India were engineered at much lower cost. The typical cost of one of these machines was less than $200. Another constraint was availability of power. So a lot of India is still off the grid or has very unreliable power. So these machines had to be engineered to work entirely off of internal batteries for the whole electoral process. Another constraint is the environmental conditions in which these machines are used, transported, and stored. They had to function correctly from the snows of the Himalayas to tropical jungle in the south. They had to be transported sometimes thousands of miles over unimproved bumpy roads. They had to deal with road dust. They had to deal with fungus and mold. And the documents for the design even mention attacks by vermin in the warehouses as being a concern. They were stored, and they're stored under generally not climate-controlled conditions in warehouses that go through this whole extreme of climb. They also had to be portable because they had to be brought to polling places all over the country, including places that were isolated from the road network. I'm told that they would ferry EVMs up the river on a boat to bring them to villages in the jungle that weren't reachable by roads. And these are amazing, amazing constraints to have to work under. One of the more interesting constraints, though, is literacy. The literacy rate in India right now is about 66%. So a third of the citizens wouldn't be able to read the names on the ballot. Complicating things further, there are hundreds of different languages in use, and not all voters are going to be able to read the script in which the names are printed if you just have one set of names and scripts on the ballot. So the answer to that problem was very interesting. What the engineers decided to do was they included a party symbol next to each candidate on the ballot, and you can see here a mock-up of what a ballot might look like. The candidates would advertise on all their posters with an image of that symbol, so the voter would just have to recognize it in the voting booth in order to make the right choice. Another constraint is the technical literacy of the voters. And you have to imagine some voters in India just are living in places that don't have power. They don't own electronic devices. The most sophisticated piece of computerized equipment that they ever interact with is the voting machine brought in for the nationwide elections. So the engineers who developed this EVM design used an incredibly simple user interface. The voter walks into the voting booth, presses the blue button next to the candidate they want to vote for, and that's it. It's one button press. The machine beeps and lights up the arrow to let you know you voted, and you move on. It's amazingly, amazingly simple. One final kind of problem that India has to deal with, or had to historically, that isn't so common in the US and Europe, is something called booth capture. And this was a common problem in India when they voted on paper ballots before the introduction of the EVMs. What would happen was in a polling place, a bunch of goons working for a particular candidate would show up, and they'd tell everyone at the polls to just go home, buddy, go home, with the implicit threat that you're going to get hurt if you don't. Then they'd proceed to stuff the ballot box with votes for the candidate they were working for. Maybe the police would arrive eventually, but the security situation was such that wasn't likely to happen soon. So the EVMs were designed to guard against that threat too. They rate limit the number of votes you can cast in a period of time. I think they'll accept. I think it's one vote every 10 seconds. So even if you take over the polling place, the theory goes, it'll still take you a very long time to significantly change the outcome of the election. So let me show you a bit more about the design and operation of these machines. They really are an incredible work of engineering to make something that would work and work well, reliably anyway, within those constraints. So the voting machines consist of two parts. There's the ballot unit you just saw on the left, and another piece called the control unit on the right. The ballot unit is in the voting booth with the voter. The control unit is attached by a cable a few feet away on a table where the election officials sit. Now the control unit is the part that actually stores all the votes, and it's amazing some of the design features here. First, it's really, really simple. There's no memory card, there's no printer. Those features in US-style machines have been eliminated. Instead, there's a series of switches, and the switches are guarded by those plastic doors you see there. And the doors are amazing. This is a physical manifestation of the different phases in the election procedures. So each door can be individually sealed and guards the set of features that are necessary at each stage. So before an election, the poll workers will clear the machine by pressing the white button. Then they'll seal the doors. That's going to prepare the machine for the rest of the election cycle. After that, every time a voter walks up, they press the big blue ballot button. This allows the ballot unit to cast one vote. At the end of the election, after everyone's voted, they'll unseal one of the doors and press the black close button. That prevents the machine from accepting any more votes. After that, there's a delay. Maybe a couple of weeks will go by between the time that votes are cast and when they're finally counted. This is because voting in India takes place in phases across the country. So the machines have to be carefully guarded for this whole period. When it's time finally to count them, they'll bring machines from all over a district together in a room, and they'll go through the counting process in front of an audience of observers and members of the public. For each machine, when it's time to count the votes, they'll open another door and press the yellow result button. Then they'll hold the machine up for the whole audience to see, and on its display screen, it will light up these digits to output the number of votes cast for each candidate. So it will first show the total number of votes, then the number of candidates, then for each candidate, candidate 1, 2, 3, and so forth, the number of votes they've received. And everyone in the room can see and write this down and add them up on their own. So it's an amazing design. This is really about as simple as you could make a voting machine, and that it works reliably under the Indian constraints is a testament to the quality of the engineers. But there's a separate question, which is whether these machines are actually secure and trustworthy. And the answer to that is not so positive. So election officials, however, before any independent parties had been allowed to analyze these machines, made a series of extremely strong security claims about them. Officials said that the EVMs were infallible, that they were perfect, that they were tamper-proof, that there was no need for technical improvement. Now, after the lectures you've seen so far, you probably understand that there's not going to be a secure system that satisfies any of these claims. These are just not the sort of claims that any knowledgeable person would make about technology. But the Indian election officials did, even after many people in India started to have some doubts about whether the machines were really perfect and infallible, particularly after one parliamentary election where some surprising results shocked a lot of people. Finally, after enough prodding from activists in India, the Election Commission of India, ECI, the nation's highest election authority, which is a separate constitutional branch of government, agreed to allow members of the public to come in to their offices and demonstrate on an actual machine how they allege an election could be stolen. So they actually held a kind of public trial. This man was one of the people who participated in the first one of these trials. The man on the right, Hari Prasad. Hari is a self-educated engineer and businessman from Hyderabad who has, through an amazing sequence of events, now become one of the country's leading experts on electronic voting. But Hari, at the time, took the ECI up on its public challenge and went into their offices to demonstrate how he thought it might be possible to cheat. Now, he'd never seen the inside of one of these machines before, so the first thing he and his colleagues, the engineers from his company, did was they opened the machine and started taking pictures and writing down notes. The election officials standing nearby started to hear them remarking, "Oh my, this is going to be much easier than we thought. We don't need all week. We'll be done today," and so forth. And at this point, the election officials started to get worried, and they immediately shut down the trial, kicked everyone out of the building, and said they were going to have to think about the ground rules a little bit more. Sometime later, they came back and announced that there were new rules that were going to be in place. Anyone who wanted to demonstrate the possibility of fraud would have to demonstrate quote-unquote normal tampering. Normal tampering was defined as tampering without opening up the machine. So I'm not sure how anyone is going to figure out how to defeat the security of a system like this without being able to know at least how it works. And you can imagine countless possibilities for insider attacks where there'd be no such obstacle to opening the machine and performing reverse engineering. But that was the ground rule set by the ECI, and so there was no realistic demonstration possible. Things changed, however, in the beginning of 2010 when Harry was approached by an anonymous source who offered to give him a real Indian EVM to study. And this source, I understand, was someone who had access to a machine legally, but had deep concerns of conscience about the security of the machines, essentially a whistleblower. Harry accepted this offer, and he and his engineers, who were based in Hyderabad, reached out to me and Rob Honkripe. We joined them in India and proceeded to study the machine. Were India's EVMs really tamper-proof? We're about to find out. When Harry and his engineers opened the machine, this is what they saw. And when we later released pictures like these, it was the first time that citizens in India were ever able to see how the machine counting their votes really worked. I don't know what the big secret was, why the Election Commission wouldn't let anyone see, because it's actually really simple. Inside, there's a microcontroller, a basic CPU. It includes a copy of the election firmware, the software that runs the elections, and that software is programmed into the chip at the factory and can't later be changed or read out. In addition, there are these smaller chips. These are EEPROM memory chips, which store redundant copies of the votes. Those large black things with the white pieces sticking out, those are just the switches that are underneath the buttons on the front of the control unit. So in addition to the main logic board in the control unit, there's the only other thing is this smaller daughter board, which is the 7-segment LEDs that showed the election results during counting. And you could barely build a simpler board. It's just LEDs and wires and connected to the main board via that short ribbon cable you see on the right. That blue thing, you might be wondering what that is at the bottom of the shot. That's actually a speaker. That's the thing that beeps every time someone votes. And after Rob and I got to Hyderabad, where Harry and his team of engineers were studying the machines, we were doing tests on the machine with the case open. And when we did these tests at night, the noise from the speaker was just so loud that if we had the windows open because of the heat, it would wake up dogs all over the neighborhood, which would start barking and raise suspicion. This project we were working on in secret. We didn't want to draw any other attention, so we just naturally covered the speaker with a piece of tape. This machine, though, the design is so simple. And when you're thinking about how someone might try to attack it, that's going to involve attacks at a variety of levels of sophistication. Before I explain to you the ways we devised to attack the machine, I'd like you to try to think for yourself, what are some of the things that could go wrong? How could criminals cheat on a real Indian EVM? So there are a lot of ways that you could try to tamper with an EVM and make it change votes. My attention was first drawn to this part, the display board, since it's probably the simplest part of the EVM design. And initially, I only found out that I was going to be able to go to India and get to be part of a team with access to one of these machines about 3 days before I left. And so I had to come up with a really simple attack to try to manipulate it. This was going to be possibly the only chance anyone would have to demonstrate the tamperability of these systems. So what I did was I went downstairs to teach my graduate level security class that I was teaching at the University of Michigan that term. And I faced a problem, which was that I had no idea how to build a circuit board that we could put into one of these machines. So I asked the students whether any of them knew how to build a board. This guy, Eric Woostrow, who was a senior at the time, sheepishly raised his hand to volunteer. When I told him we only had 3 days, he looked at me like I was crazy, but he still agreed to do it. And partly for that reason, Eric is now one of my PhD students, and he's been a big help in the preparation of this course. Another problem with any kind of attack that's going to involve tampering with the electronics in the machine is that you'll have to have physical access to them. Now, you can think of various ways that a criminal could get that kind of access. Maybe the criminal is an election insider. We've talked about insider attacks and why they're a huge threat already. Another possibility is that the attacker could try to manipulate the machines between elections while they're in storage. In India, these EVMs are kept in vast warehouses that might have thousands of machines in one place. They're usually not in the highest security facilities. They might be part of a high school or an old industrial facility. You can easily imagine how criminals might be able to bribe or coerce the guards to get into one of those warehouses when they'd then be able to tamper with thousands of machines in one shot. The Indian machines are also protected with tamper-evident seals, but they're not the highest tech kinds of seals. You can see a couple of pictures of them here. The seals on the machines consist of candle wax, paper, and string. And I'm sure all of you can think of some ways you might be able to tamper with these. So Rob and I got to Hyderabad and proceeded to test out the board Eric had built on the real machines. And it worked almost on the first try. So here's the board Eric built. It looks almost exactly like the real display board found in the Indian EVMs, except underneath these LEDs and that plastic spacer, we've added some additional components. On the left, you see that square chip. That's an embedded microcontroller, a microprocessor. What it does is it intercepts the signals the machine is trying to send to the board to tell it which results to display, and it can rewrite them on the fly. This is what we call a man-in-the-middle attack, but it's implemented in the electronics of the board. We call this attack a dishonest display board. And the dishonest display can replace the real results with whatever results the criminal wants to show. Here's a picture of the dishonest display inside the real EVM, and here's a comparison between the regular display board and the dishonest board. A simple inspection is not going to reveal any differences. The way the board works is it watches when votes are being counted and moves votes from all the other candidates to the preferred candidate of the attacker. This is a little bit tricky because we have to make sure the total still adds up to the right number. Otherwise, if they're just counting the number of voters, they might detect the attack. But we were able to do this with some clever software heuristics. So you might imagine that attackers who took over a warehouse or something would replace the real boards with dishonest displays in thousands of machines, but that's a lot of effort to go to for just one election. If they wanted to leave the boards there and cheat potentially in all future elections, they'd need some way to tell the board which candidate number to favor. You won't be able to predict years in advance which ballot position your candidate will be on, but you will then need some way to communicate to the board who to cheat for. So there are several ways you could do this in the Indian system, but the one that we actually demonstrated involves that other chip to the right of the M. That's an embedded Bluetooth radio, and it talks to an application on a smartphone. So we built this prototype application that lets you control the dishonest display. It lets you pick which candidate you want to win and what fraction of votes to shift to them. So someone could be at that counting session in public where they're holding up the machines and use a smartphone with an application like this to signal to all the dishonest displays who should win. The second attack that we demonstrated has to do with these chips. These are the memory chips that record the votes and vote totals inside the machine. Harry and his team of engineers had reverse engineered the data format, the structure of the information stored on these chips, and they were able to find out that there was no cryptographic protection to the information stored on them. They were able to come up with an attack where if you hooked a laptop up to the voting machine, you could rewrite the votes to reflect whatever totals you wanted. But this wouldn't be very practical in the field. It takes maybe 15 minutes per machine to set up and requires bulky, sensitive equipment. So we consulted with the team in Hyderabad after I was back in Michigan, and we came up with a design for a new attack that would be a much more compact form of manipulating the votes in the memory chips. This is what we built, and I'm holding one of these devices right here. This is a device we call Clippy. Clippy attaches directly to the memory chips inside the voting machine. And with the machine powered on, it rewrites the votes stored in the chip to be in favor of whichever candidate the attacker wants. You just turn this knob here on top of the device to pick the candidate you want, attach it to the chip, and then the busy light comes on and flashes orange for a couple of seconds. Then the done light lights green to let you know you're finished. You detach the device, move on to the next machine. So Clippy represents an electronic form of the booth capture attack. If the criminals can take over a polling place, they can open up the machine and stuff as many ballots into the ballot box as the virtual ballot box as they want using a device like this. These are low cost. They would cost just a few tens of dollars to make. They are simple electronics. There are probably 1 million people in India who could make one. And they are so simple to use, you could have your uneducated goons carry out the attack. So either during the polls or during that time between when votes are cast and counted, which can be a couple weeks in India, an attack like this could manipulate all the votes stored in the machines. Then there's one more security issue that leads to some other possibilities of attacks you might have thought of. And that has to do with that secret software that's baked into the chip, the actual software that's counting the votes. How do we know the software in the machines is honest? Well, it turns out that there are several impediments to being able to trust that software. First of all, the Election Commission of India, the country's highest election authority, doesn't own the source code. The software is owned by the companies that made the machines. Second, the Election Commission has never even seen what's in the source code. They're just taking it on the word of the engineers who developed it. One of the Election Commission's chief technical experts told me that only 3 or 4 guys at the companies that made the machines know what's in the code. But he says there's nothing to worry about because he's talked to those guys and they seem trustworthy. You can imagine that those engineers, even if they are trustworthy, they might be bribed, they might be coerced, someone could threaten them or their families in order to try to smuggle in some vote-stealing code into the chips. But because the chips are implemented in a way that makes it virtually impossible to read out the code after the machines are in the field, there's no way to tell whether the software that's actually in them matches what's supposed to be running or whether the software inside them is honest. This just means there's no transparency whatsoever to the process of counting votes in these machines. It creates a tremendous threat for possible dishonest software corrupting the election results. So our study concluded that the paperless EVMs used in India are, in fact, tamperable and insecure. Committing fraud with the EVMs would take basic electronic skills, not rocket science. And this kind of fraud could take place either while the machines are in storage, during polling, or between polling and counting. Detecting fraud with these attacks could be difficult or impossible, especially if they were carried out with the help of dishonest election insiders. For these reasons, we concluded that the Election Commission's claims that the machines were perfect, tamper-proof, and in no need of technical improvement were totally without basis. We'll see how the Election Commission responded to these findings in the next segment. When we had finished our study of the Indian EVMs, we published a scientific paper detailing the findings as well as a website and YouTube video that would explain to non-technical people what the problems were, that the EVMs could indeed be tampered with. At the same time, Harry went on to TV in the local region of India where he lived and gave live demonstrations using the actual EVM from the anonymous source, where he showed our display attacks and our clippy memory manipulation attacks to prove to everyone that tampering was possible. The Election Commission responded by saying that these findings were false, that either we didn't have a real machine or what we showed wasn't true because the machines were tamper-proof and perfect. But gradually, as the news percolated through Indian society and people came to read our claims and see our videos, there started to be wider doubt about whether what the Election Commission was claiming was actually true. Behind the scenes, however, the reaction was significantly more tense. We saw stories like this come out that alleged that Harry had been part of a foreign conspiracy to discredit India's democracy, and that it was being investigated by the Indian intelligence agencies. We got further interaction with the Election Commission when we invited some senior technical staff from ECI to come to the U.S. for the Electronic Voting Technology Workshop, which is one of the major scientific venues for research in this area. And we had a debate between them and me and Narasimha Rao, an Indian election activist who had written a book about the EVMs. Now, this discussion, this debate, was one of the most amazing, one of the most incredible discussions I've ever seen at a conference. To give you a sense for it, a fist fight almost broke out at one point. I'll put a link to it up on the course website, but it's really something you should check out if you have time. The upshot of it was that the Election Commission was still maintaining their claims that the machines were perfect, but they were starting to feel the heat. And when an international audience of researchers all started to raise very serious questions and not buy the claims that the machines were perfect at all, they knew they had a problem on their hands. A few days after that panel, the tension rose considerably. When Harry received this, it was a summons from the police. They were investigating the theft of the EVM, and they wanted to bring him in to Mumbai for questioning. Now, Harry and his lawyer were communicating with the police about this for several days after, but they apparently didn't want to wait, because one night at about 4 in the morning, Harry got a knock on his door. And a large squad of police officers rushed into his apartment and hauled him away. He was taken across the country by car from his home in Hyderabad to this particular police headquarters in Mumbai, about a 14-hour trip. Luckily, they left him with his cell phone, perhaps because they wanted to see who he'd tried to contact. But one of the people he called was me. And I have a recording of what he said to me that day from the police car here for you to hear.
I'm okay, thanks. I'm okay. We just reached Mumbai. In another 20-25 minutes, we'll be reaching the police station. Police came to my house at 5:30 in the morning, saying that they're going to take me into custody, as I couldn't revert back to them on the anonymity. In the sense, like, I didn't disclose who has given me the mission. They said, like, if you want to get out of this, you have to find who has given you, and you get out of this issue, then nobody will touch it. The police are getting pressure on the top, so obviously they can't do anything. They have no other option than arresting me. The only thing what I want to say is this kind of intimidation will hit the hearts of volunteers, and no volunteer will come forward if this kind of thing happens in future. That's the reason I'm going to take it on, and I'll face it so that the volunteers get inspired by me. And the ultimate goal is we have to achieve that these machines are not fit enough for the elections. This is what I'm thinking, and I want to say whatever research we have done or whatever work we have done is right with all my heart. Thanks for your concern.
Just listen to his voice. It's so amazing. Here's a man being hauled off across the country by the police for something he believes in so deeply. As he says, he's not going to turn over the anonymous source. He's going to keep his promise to protect that identity. He has to, because otherwise, who's ever going to come forward again and volunteer to blow the whistle on government corruption or false claims if they know they're just going to be revealed to the authorities the first time the police come calling? Harry was told by the police that that's all he had to do to make all of this go away. Just name the anonymous source. But he kept his promise not to reveal that source, even though he was held by the police for more than a week without getting to see his lawyer, even though he was interrogated several times a day. All he would say when they asked him, "Who gave you the machine?" was, "I don't remember." Now, in India, you don't have a right to remain silent, but apparently people are willing to believe that you can will yourself to forget a thing like that. And so that's the story that he maintained. After about a week, he finally got to come before a magistrate, and he was released from the police station, but had to remain essentially under house arrest in Mumbai for about another month. He couldn't go back to Hyderabad to see his family or to run his business. Fortunately, Harry soon received a call from one of the best criminal defense lawyers in the country, who offered pro bono representation and defense. This man was the son of the man who had defended Indira Gandhi's assassins. Of course, they hanged for it, but we all hope that Harry would fare better. Harry's arrest and his refusal to name the source made him into something of a celebrity in India. And during the time that he was held by the police, there was a tremendous amount of coverage, and people really started to pay attention to the findings that we were claiming, that the machines could be tampered with. Eventually, several weeks later, there was enough change in attitude that all of the political parties in India came together in Delhi, had an all-party meeting, and asked the Election Commission to investigate the findings and to find some way to add a paper trail to the EVMs to increase voter confidence. They basically asked the ECI to do exactly what we recommended in the paper and add some kind of transparent paper record to the EVMs. To our surprise, the Election Commission agreed, and over the time since then, they've been making amazing progress towards exactly that end. The Election Commission formed a special committee to study ways to add a paper trail, and even now they are prototyping and testing electronics and a new version of the EVM that add a voter-verifiable paper audit trail to the process. This would be a way to ensure that the electronics aren't cheating and that the system is counting with integrity. But what happened to Harry? Shortly after Harry was released from house arrest in Mumbai, he received a call from the Electronic Frontier Foundation. They named Harry a 2010 Pioneer Award winner, their highest honor for great work in civil liberties and in tech issues. They recognized Harry both for his work to reveal the problems with electronic voting in his country, and for the courage he showed maintaining his promise of anonymity towards his source. Harry got to travel to the U.S., where we met for the first time in my native country. We got to visit California, where he would accept the award at a ceremony in San Francisco. A few months after this, his case finally came to a conclusion when Harry got to go before a judge who declared that this man had done a service for his country, and that if anything, the government should be investigating the problems that he had pointed out, not harassing him or the sources who had helped him. So everything seemed good. Harry was out of trouble. The Election Commission has, as they continue to, they've continued to, been working to implement a paper trail to rectify many of the problems we pointed out. Everything seemed good until, that is, the next time I went back to India. But that's a story for the next segment.